Right, I'm going to carry on going through this engineering maths and modelling CIVE1560 June 2024 exam question on vectors, and this is question 4b. 4b. It's a question using vectors to do mechanics, to take moments to represent forces in terms of vectors. Very typical, so pay attention because it's got many of the features in many questions that you'll see in an exam. Let's just take some features out of this this question. Now, it says that there's a force acting down at this hook, and I'm just going to label that magnitude F, and that force is causing this moment about point B. Now, those are important things to note straight away. And we know that moments, and I'm going to write M as a capital M, the moment vector is equal to the force vector F cross product with a position vector, and in this case this position vector is AB, the line AB on this diagram. Okay, this is a calculation which we're going to refer to when we're determining when we're making use of this and determining the mass. But let's just go back a little bit. So I'm just going to let me go back a little bit. So we're saying that we've got a mass acting down, and it's acting down with a gravity of 10. So this force acting down, and maybe I'll colour that in green, this F is equal to mg, which equal to m times 10, because g is 10. We need to write this in terms of a vector. This is just a magnitude at the moment. We'll need to turn all the forces in each of the struts into a vector. The question also says we've got FAO as a vector. If that's the force in the strut. As a magnitude, not a vector. We will calculate a vector in a moment. We've got the force FAC, AC, and we've got the force FAB that we're going to use later. When we write all these forces in vector form, because it's all in equilibrium, we know also that the forces in vector form will sum up to be 0, or the force due to the hook will equal to the force vectors FAB plus the force vector FAC plus the force vector FAO. So at some point we're going to need to calculate these and use that equilibrium, and we're going to, we're also going to use this moment calculation. So how do we go about doing this? Well, the first thing we need to do is to, on any question involving geometry, is to write out the coordinates of all the points we know. Now we know that A is equal to 2 minus 2, 6. We look at the coordinates. Be sure you know this. This is absolutely key. You need to get these coordinates right, so let's do them carefully. B is equal to minus 4, 2, 0. C is equal to 0 to 0. We then need to calculate the vectors in the direction, and we'll do them. AB is equal to B minus A, which is equal to, and get this right as well, because it's easy to get your signs wrong here, minus 6, 4 plus 4, minus 6. I'd recommend you do this, and you do it to check it again, and you do it again to make sure you've got all your signs right. AC is equal to C minus A, which is equal to minus 2 2 minus 2 is 4 minus 6, and AO is equal to O minus A, which is in fact just the negatives of A, minus 2 to minus 6. We're going to need the unit vectors in the direction of each force. So the unit vector in AB will be the unit vector of AB, unit vector, is equal to AB over the magnitude of AB. The magnitude misdrawn that. That should be AB magnitude. The magnitude of AB is equal to the square root of 36 plus 16 plus 36, which equals root 88. Now let's do the other magnitudes. The magnitude of AC is equal to the square root of 4 plus 16 plus 36, which equals root 56. Magnitude of AO is equal to the square root of 4 plus 4 plus 36, which equals to root 44. So we can now write our our unit vectors. U AC is AC over the magnitude of AC, and UAO equals AO over the magnitude of AO. Okay, we can write these down explicitly now, completely. UAB is equal to, and we'll write them with the surds outside, it's much more convenient, minus 6, 4, minus 6, UAC equal to 1 over 56, rooted, times minus 2, 4, minus 6, UAO is equal to 1 over root 44, minus 2, 2, minus 6. The one thing we have left, the unit vector in the direction of our force acting down, the unit vector of our, and I'll call that unit vector of F. Well, it's acting down, so it's just 0, 0, minus 1. So we can calculate now our force vectors, and we can do this by here. The force vector AB is equal to FAB, and not a force vector, a magnitude, times that unit vector UAB. I'm not going to write them out in full just now because we don't need them quite now. The force vector AC is AC, that magnitude times UAC, and the force vector AO equals magnitude of AO multiplied by UAO vector. Now the force vector F, we can write this vector now because we know that F is equal to mg times by 0, 0, minus 1. And g is 10, so we can say that is 0, 0, naught, naught, minus 10 m. So this is our force vector. We'll look at that again. Now what's the question say? The question says that the magnitude of m is equal to, and let's see why the question says that, 8 root 13 kilonewton meters. 8 root 13 kilonewton meters. Now we could say that is 8,000 root 13 newton meters. Remember, the magnitude of m. What we can calculate though now is m, this moment, which is equal to the force F times by r, where r is AB. So F times AB vector. So times cross product. So here. So we can write that again. M is equal to the determinant of I, J, K. We write down the vector AB, and AB is minus 6, 4, minus 6, and F is our 0, 0, minus 10 m, the mass of the hook. And we can expand that. I times the determinant of 4 minus 6, 0, minus 10. Just do a quick check. Yep. Minus j times the determinant of minus 6, 0, minus 10 m, plus k times the determinant of minus 6, 4, 0, 0. Expanded that, we have I times minus 40 minus j times 60 m, sorry, written that wrong, that's actually 40, this is important, 40 m minus 60 m plus 0k, so we don't need to write that, but we'll leave it in there. So m equals minus 40 m I minus 60 m j plus 0k. Okay, so what have we got there? We've got the moment m. We need to calculate, we can calculate the magnitude of this moment, which is the square root of 40 squared m squared plus 60 squared m squared. If you expand that, we will see that this is equal to m root 5,200. But we're also told that m from the question, let's make this more clear, this moment, which we just calculated as lowercase m root 5200, is equal to 8,000 root 13. Our unknown here, the mass of the hook, is then equal to 8,000 root 13 over 5,000 root 5,200. You can put that in your calculator and that all comes out to 400 kilograms. Or you can do it by looking at your surge. We've got 8,000 root 13 over well, there's various ways of doing this, but we could write root 400 root 13, cancel those, and that'd be 8,000 over root 2 root 4 root 100, and we know that that's that can easily cancel down to 400. Okay, but the question was to calculate m, this 400 kilograms. As you'll see, this is quite a complex question. We've done some extra calculations before we got to this point, and they'll help to do the next parts of the question. But this is the answer. Right, what was the next part of the question? It says, let me see, express the forces along AO, AB, AC in 3D Cartesian vector formats. Well, these are dead easy because we've already calculated our unit vectors. It's these three that we need to write down, and that's the answer for part B. So let's remember those. Root 1 over root 8. So for part B, FAB equals, well, the force, let me just write that correctly. The force, the FAB, UAB, which equals FAB times 1 over root 8 times, I don't remember that, minus 6, 4, minus 6. Minus 6, 4, minus 6. FAC as a vector equals FAC as a magnitude times the unit vector UAC, which is FAC over root, let me see, 56 minus 2, 4, minus 6. 56 minus 2, 4 minus 6, let's check that, minus 2 minus 4, and the last one, vector AO, is AO, UAO, which equals FAO, root 44 to minus 2, 2 minus 6. Minus 2, 2 minus 6. So those three vectors are equal to the force vector F is equal to FAB plus FAC plus FAO. These are vectors, remember. Now, that's part B. That's the answer to part B. Part C, the question says, using static equilibrium condition set up at A, so point A here, set up a system of three simultaneous equations for the unknown forces, those three unknown forces. I write them as a matrix equation. So what that is saying, it says resolve in part C is asking to resolve in x, y, z. Now what we have in these equations above here are x terms, y terms and z terms. So we can write out equations for all the x terms, and we can write out equations for all the y terms and then all the z terms. It's as simple as that. It's really just rewriting what we've already done. So let's take x direction. We'll say that have I got these correct? Let me see. Oh yeah. Minus 6 FAB over root 88 plus minus 2 FAC over root 56 plus minus 2 FAO over root 44 is equal to 0. That's just this vertical common here. And we can do it for the y direction. So in the y we have this column here, 4, 4, 2. So we have AB over root 88, AB over root 88 is 4 plus 4 FAC over root 56 plus 2 FAO over root 44 equals 0. So there's nothing in the y direction. And then we have z, and this time we're going to look in this z column, minus 6 FAB over root 88, minus 6 and minus 6, so minus 6 FAC over root 56 plus, well, it's minus 6 again, FAO over root 44 is equal to 0. I probably should just write x here at the top again. So what was x? Minus 6 FAO over root 88 minus 2 and minus 2 plus minus 2 FAC over root 56 minus 2 FAO over root 44 equals 0. Now I've made a mistake here. This is not a 0, is it? This is the f term. This is equal to 10m minus 10m, which equals 4,000. Okay, now that's the answer to question B, but it says write it in a matrix form. So we can write this down as a matrix where the in the columns here we have FAO over root 88, FAC over root 56, and FAO over root 44. This right hand column will be 0, 0, minus 4,000, and the matrix will look like minus 6, minus 2, minus 2, 4, 4, 2, minus 6, minus 6, minus 6. And that is part C of this question. So you'll see quite an involved question, lots of places to make small errors. Practice getting it right.